The Gauss-Jordan method that I talked about on two separate lectures might have seemed just like an exercise, but I want to give you a little application for it. What I'm going to show here actually could be a linear programming problem, but I'm going to show it as an exact solution and using Gauss-Jordan. So in this problem, you want to ship some things. You have three products that need to be shipped, but you have some limitations on the poundage, the area, and also the insurance that you can afford to ship these. And so you'd like to know how many of each item you want to ship. And what you have is, say, 6,000 cubic feet of container space. It can hold a maximum of 11,000 pounds. And the insurance that you have is $36,900 worth of insurance. So you want to insure these things adequately, and of course you can't go over the pound or the space limits. This chart gives you the information about the products. So we have three products. I'm calling them X, Y, and Z. And product X occupies 10 cubic feet, one item of product X. Product Y only covers 8 cubic feet, and then product Z takes up 20 cubic feet, so it's bigger than the others. As far as weights go, product Z is 40 pounds, Y is 20, and product X is 10 pounds. And then the individual worth of each product, $100 for product X. Product Y is only worth 20. Product Z is worth $200. And listed in this column are the maximum available for the volume, weight, and the insurance. So you could take this, like I said, as a linear programming problem and say that the 6,000, 11,000, and the 36,900 are maximums, and you want to make sure that you stay less than that maximum. But here it's going to come out even, and I just want to use this to show the Gauss-Jordan method anyway. So what I'm going to do is take these and write them as a system of linear equations. So when I look at the first line, if X, I'm going to let X be the number of product X. I'll make it do double duty here. So 10 times X, because each weighs 10 pounds, 10X is the total amount of, of volume that's going to be taken up by all the X products that I ship. And then 8Y, Y being the number of product Y that I ship, that's how much volume that will take up. And Z's take up 20 times the number of Z products that I ship. And I'm going to say that has to equal 6,000 cubic feet, because I'm going to be able to fit everything in. Okay, so here was my first equation, and this has to do with the volume. And now if you look at the weight, if I have X number of product X's that I'm shipping, I have to multiply by 10 to get their total weight, because each one weighs 10 pounds. So here's my equation for the weight, and then using the value, I want that to be equal to the insurance that I have available. So here's a system of equations. They're linear equations, and they're very conveniently in standard form. So now I'm going to write those as a matrix equation. So here's a matrix equation. You remember this was your coefficient matrix, the first one. And the X, Y, and Z is the vector of unknowns. And the third matrix is the solution matrix. And this is a matrix equation. It has an equal sign. So out of this matrix equation, I form the augmented matrix by taking the coefficient matrix and the solution matrix and putting them together. Again, in practice, I usually put a dashed line here just for my sake, but the word processors can't do that. Now I'm going to go through the steps of Gauss-Jordan to find the number of product X's that I should ship, the number of product Y's, and the number of product Z's. So I started with my original matrix. Let's go back and look at that for 1 minute. Recall that the goal for Gauss-Jordan is to turn the coefficient matrix into the identity matrix. So this is where we're going. And then what I'll get over here in this last column is this answer or solution for X. This will be the solution for Y, and here's the solution for Z. So once I have this as the identity matrix, then what I have in this last column are the solutions. And the way I create that identity matrix is that I can divide or multiply a row by any number as long as it's not 0, and I can add and multiply rows together. Add and subtract rows together, and I can also switch the order of rows if that will help me. In the first step, I capture this 1 right here for my identity matrix, and to do that I had to divide the old row 1 by 10 and then store the results in row 1, and I get this matrix. Now remember, when you do Gauss-Jordan, you never go back to the original matrix or any one before. It's just a stepwise process. You've created a new matrix and now you change that new matrix. So I want to get a row of zeros or column of zeros under the 1. This is what I'm going for here. So I take row 2 and subtract 10 times row 1, and that ought to make a 0 there, and it does. And then the rest of the row is 12, 20, and 5,000. And then I take row 3 and subtract 100 times row 1 and put the result in row 3. That's what I'm showing here. And now I did 2 steps at once here. But now by doing this, I have created the first column for my identity matrix. And now I'm going to look at something here. I didn't have an opportunity before to demonstrate switching rows. But look at this for a minute. Remember where we're going with this. We want to go 1, 0, 0 and the answer for x. And then 0, 1, 0 and the answer for y, and the 0, 0, 1 and the answer for z. Okay, this is where we want to go. So far we've achieved this, but look at the matrix. You see, this has a 0 here, this needs a 0 here. I can save myself time by just switching these rows. That's okay if you switch the entire row. So that's what I do next. So here I'm switching row 2 and row 3, and now I'm going to write again my goal right here so you can see it, see where we're going. This would be the answer for x, answer for y, answer for z. Okay, so now let's see what we've got. I wanted this, I've got that. I needed a 0 here, I got that. Don't go work for that 0, but if you can get it by switching rows, then do that. Okay, what do I want to do next? Well, here's what I need to do is work on this column. All right, so I need that minus 60 to become a 1, and I need the 12 to become a 0. So what I did is 0 out that the 12. Ordinarily I would have done it another way, but I just decided to show you that you don't have to be real lockstep with this as long as you don't get too far off from the pattern. Okay, so now in this case I have the first column, I have this 0 and this 0. Now the minus 60 and the 20 have to turn into 1s, and that's what I'll do next. So to turn the minus 60 into 1, I just divide all of row 2 by minus 60. To turn the 20 in row 3 into a 1, I just divide the entire row 3 by 20. And now I have quite a bit of my matrix. I'll just point out what I have here. I've got the first column, then I have this 1 and a 0, I've got the 1 here, and I even have a 0 up here. So the only problem is to make the 0.8 into a 0 and the 2 into a 0. Well, first thing I'll do is make the 2 into a 0. Well, you could have done it either way, but I do that by subtracting 2 times R3, and now I have a 0 that I wanted. And now let's see, I've got to make the 0.8 turn into a 0 also. And that's done by using row 2. And now I have the identity matrix, and the values here are the answers for x, y, and z. This means to fill up all that cargo space, all the container space, and use up all the 11,000 pounds that were available, and have the value of the product equal to the insurance policy of $13,900, then I would ship 494 items of product X, 385 of product Y, and 19 of product Z. So that's just an application of Gauss-Jordan to a business problem, so you can see at least some application of that method.